Hello, Matthews Gatos here. Welcome to Chapter 2, Lesson Number 2, Equivalent Forms of Rational Expressions. In this lesson, we're going to learn about what is an equivalent form. This is really going to help us when we're simplifying and when we're adding and subtracting. So we've learned about equivalent forms of rational numbers before. For example, if you wanted to take 10 over 15 and write it in simplest form, you would divide the numerator and the denominator by the greatest common factor, which is 5. So I'm doing it to the numerator and denominator, which is fair. 10 divided by 5 is 2. 15 divided by 5 is 3. So this would be an equivalent fraction to 10 over 15. It would just be in simplest form. Now, the reason that these fractions are equivalent, even though they look different, is because we did the same thing to the numerator and the denominator. Because 5 over 5 is really 1. It's a form of 1. So by dividing numerator and denominator by the same number, we can put it in lowest terms, and these two fractions will be considered equivalent. Let's look at another one. Say if we wanted to create another equivalent form. Now we can divide, but we can also multiply. So say I multiplied numerator and denominator by 2. I would get 20 over 30. So since I multiplied the numerator and the denominator by the same value, these fractions are also equivalent. Equivalent meaning they have the same value, they just look different. So this is not in your workbook, but just follow along with me. I want to look at all the ways we can create an equivalent fraction. So let's start with 5 over 10. If I have 5 over 10 and I divide the numerator and the denominator by 5, being fair, doing it to both, I'm going to end up with 1 over 2. So are these fractions equivalent? Well, what I can do is look on my calculator to see 5 out of 10 is 0.5 and 1 out of 2 is also 0.5, so these fractions are equivalent. Let's try this one here. So I have 5 over 10, but this time I'm going to multiply by 5. So multiply the numerator and denominator by 5. So I'm being fair because I'm doing it to both, so I end up with 25 over 50. So my question is, are these equivalent? And again, we'll go to our calculator to check that. So you can see 5 out of 10 is 0.5. and 20 out of 50 is also 0.5. So it looks like by dividing and multiplying numerator and denominator by the same number, I get an equivalent fraction. Well, let's try adding and subtracting. So here I'm going to add 5 to the numerator and denominator. So I'm being fair, I'm doing it to both, and I'm going to end up with 10 out of 15. So my question is, are these equivalent? So if I put this into my calculator, 5 over 10 is 0.5, but 10 over 15 is 0.6 repeating. Not the same value, they're not equivalent. Let's try subtracting. So I'll subtract 5 to the numerator and the denominator. I'm being fair because I'm doing it to both. So 5 take away 5 is 0, and 10 take away 5 is 5. So hopefully you can see right now, those are not equivalent because 0 divided by anything is 0. So these are not equivalent. So you cannot make an equivalent fraction by adding or subtracting numerator and denominator by the same number. Even if you're fair, it won't create an equivalent fraction. So the only way I can create an equivalent fraction is by multiplying and dividing. Okay, another way of simplifying a fraction, instead of finding the greatest common factor right off the get-go, is to break it down into its factorization and cancel common factors. Okay, so here I broke it down into 5 times 2, 5 times 3. The 5's cancel, I'm just left with 2 over 3. So these are equivalent fractions, which again are fractions that look different but have the same numeric value. So let's try to create some equivalent fractions. So if I have 18 over 42, I want to create an equivalent fraction by dividing numerator and denominator. I can divide it by anything at all. Let's say I divide it by 2 because they're both even numbers. So 18 divided by 2 is 9 and 42 divided by 2 is 21. These two fractions are equivalent, not equal, equivalent. So meaning that they have the same numeric value, they just look different. We can also create equivalent fractions by multiplying numerator and denominator by the same number. So let's say we do that by 2. So 18 times 2 is 36. 42 times 2 is 84. So these fractions are equivalent. Now, another way that I can do this is by factoring and dividing common factors. So I have to look at the prime factorization of 18. So looking at 18, I can break that down into its prime factorization, which is 2 times 3 times 3. And then I'll do the same thing for 42. I'll break it down into its prime factorization, which is 2 times 3 times 7. So you can see 2 divided by 2 is 1, 3 divided by 3 is 1, and that's equal to 3 over 7 in the final step. So again, these fractions here are equivalent. Look different, but have the same value. So let's look at equivalent forms of rational expressions. We'll throw some variables into the mix now. So if we have 2x over x squared plus 2 and 2 over x plus 2, if we put that into my graphing calculator just to come up with the table of values, when x is equal to 1, in other words, I substitute each of these x values with 1 and this x value with 1, you can see I end up with the same result. Same thing happens when I do that for 2 and for 3 and for 4. So what I can say about all of these values of the rational expression when I replace it by 1, 2, 3, or 4 is that they are equal for every value, meaning these fractions are equivalent. So these forms are known as equivalent fractions. So here's how we're going to do to prove two fractions are equivalent. Step number 1, we're just going to factor. So for example, I have 2x over x squared plus 2x. So you can see I have a common factor of x. So if I factor out an x, writing your GCF up first, I have x squared divided by x, which is 2x's on the top, 1 on the bottom. 2 take away 1 is 1, plus x divided by x is 1, and you're just left with 2. So you can see now I have 2 times x in the numerator over, and remember when we have number and variable side by side, that just means multiply, x times x plus 2 in the denominator. So x divided by x is 1, and what I'm equal to is 2 over x plus 2, which is what I was trying to show was equivalent. Okay, so when this fraction here is written as this, it's said to be in lowest terms or simplest form because there are no other common factors. Now, a big mistake that some students like to make, let's look at this. This was 2 over x plus 2. So some students like to cancel those two out, but you can't do that. The reason you can't do that is in the denominator, let's write that again. In the denominator, this is not a 2. It's not just a 2 by itself. This 2 is attached to the x plus 2. So the x plus 2 is one whole term. So it's one whole term. So when you're canceling, you're only canceling like terms. So again, it's not a 2 by itself, it's an x plus 2. It's all attached. So the only thing you can cancel with is an x plus 2. Let's talk about non-permissible values. Okay, so if we look at this table, before and after, you can see that before I simplify, I have 2 errors in my table for this fraction, which is when x is equal to 0 and when x is equal to 1. So this fraction is not defined when x is negative 2 or 0. But look what happens after I simplify. After I simplify, I only have one error message, and that happens when x is negative 2. So the reason that the values in B and C result in expressions not being defined is because we can't divide by 0. So if x was 0 or negative 2, the denominator would equal to 0, and you can't divide by 0. So restrictions are always important. But these two are equivalent, and you'll see that before I simplified, I had 2 non-permissible values, and after I only had 1. The reason is because I stated them before I simplified and after. So when you're doing a question yourself, you want to state your restrictions before you simplify, because these ones here had different non-permissible values. Okay, so this is equivalent to this. So this rational expression here should have the same non-permissible values as the original rational expression did. So when I write it into lowest terms, it does have those restrictions. So the moral of the story, state your restrictions before you simplify. Super important. So when we're simplifying an expression, this is the steps I want you to follow. Factor, state restrictions, and then simplify in that order. It's super important that you state your restrictions as soon as you factor. So let's try an example. I have a new one that I want you to do, so you can replace the one that's in your workbook. I'd like to write an equivalent form of the rational expression 16x over 12x minus 8. So the first one I want to do is by just dividing the numerator and denominator by something. Let's divide it by a number. Let's divide it by 2, for example. So I'm going to have 16x divided by 2 is 8x. Now, when I'm dividing the denominator by 2, I have to remember to divide everything by 2. So 12x divided by 2 is 6x. Take away 8 divided by 2 is 4. Now let's try and write an equivalent expression by multiplying the numerator and denominator. Let's say multiply it by 2. So 16x times 2 is 32x. 12x times 2 is 24x minus 8 times 2 is 16. Now, in the last step, let's do this by factoring and dividing out common factors. So what I want to do is I look at my numbers 16, 12, and 8. I want to find a number that goes into all of those numbers. Now, if you're stuck, the calculator can only do 2 at a time, but I just want to show you a little trick. If you weren't too sure what the GCF of those numbers are, I'll show you how you can do it on your calculator, even though it has 3 numbers. So I'm going to go into math, over to number, and down to greatest common factor. And I'm just going to do the GCF of 16 and 12. I'll start with 2 numbers, because that's all you can do is 2 numbers. So the GCF of 16 and 12 is 4. So I want to check is if I take this GCF with my third number, that will give me the GCF of all 3. So math, over to number, down to option number 9. I'm going to take the greatest common factor of the first 2 numbers and put it with the third number. And I still get 4. What that tells me is that 4 is the greatest common factor of all those numbers. So let's go back here, and I'm going to factor out a 4 from each. Okay, look to see if there's any other greatest common factor. So this one has an x, this has an x, but this does not have an x, so it is not a common factor. So it looks like just 4 is the common factor. So 16x divided by 4 is 4x. 12x divided by 4 is 3x. Take away 8 divided by 4 is 2. Okay, so now that I've factored it, I'm going to state my restrictions. So my restrictions are that 3x minus 2 can't be 0. So let's look at what happens when it does equal 0. Adding 2 to both sides, I get 3x equals 2. Dividing both sides by 3, I get x equal to 2/3. So that is my non-permissible value, which means my restriction is x can't be the non-permissible value of 2/3. Okay, now that I've done that, I can cancel out my common terms. 4 divided by 4 is 1, and I'm left with 4x over 3x minus 2. And since I've divided out the greatest common factor, I can say that this is simplified. It is in lowest terms, and I stated my restrictions before I simplified. Okay, I can always check on the calculator to see if they are in fact equivalent. So I can check if 8x over 6x minus 4 is truly equal to 4x over 3x minus 2, remembering that the check always happens in the table, and you can see that they are equal, so I know those are equivalent fractions. Okay, let's try another one. Which of the following are equivalent forms of the rational expression 6 over 2x minus 1? So what I'm going to do for each one of these, I'm just going to write this out 4 times, is I'm going to compare this fraction to each one of them just to see if they are equivalent. Like, what did I do to the numerator to get the new numerator? And then I'll do the same to the denominator to see if they are in fact equivalent. So here's what I mean. If I look at 6 and I end up with 12, what I did to 6 is I times it by 2. So since I multiplied by 2 to get the numerator, I would have to multiply this entire denominator by 2 to get something that was equivalent. So 2x times 2 is 4x. That's good. But 2 times 1 is not 1. That's wrong. So this is not equivalent. Okay, let's look at the next one. So to go from 6 to negative 18, I would multiply by negative 3. So if they are equivalent, I would multiply the denominator by negative 3 as well. So 2x times negative 3 is negative 6x. Negative 1 times negative 3 is positive 3. So they switched around because it's a negative. So this is equivalent. Let's look at the next one. To go from 6 to x squared, I multiplied it by x squared. So to be fair, I'll multiply the denominator by x squared as well. So 2x times x squared, 2x cubed. Negative 1 times x squared, not negative x. It's missing a square. So that is not equivalent. And in my last one, to go from 6 to 3, I would divide by 2. So I need to do the same thing on the bottom. I need to divide this whole thing by 2, each part by 2. So 2x divided by 2 is x, but 1 divided by 2 is not 1. So this is not equivalent. Now this question, the entire question could be done on your calculator. Let me show you how. So I put the original question into y1, and here's each of those other rational expressions. Remember, the check always happens in the table. So looking at the table, I'm looking at which one of these is equal to y1. And it looks like the only one that matches up for the permissible values, because there are some restrictions, is y1 equaling to y3. So you can see negative 6, negative 6, 6 and 6, 2 and 2, 6 fifths, 6 fifths, 6 sevenths, 6 sevenths. So those are equal. So I know that the answer would be what was in y3, which is this one here. Okay, let's try this one here. Consider the rational expressions 4 over 2 minus x and 8 over 4 minus x. John evaluated each expression for 0. Based on his answers, he concluded that the rational expressions are equivalent. Comment on his conclusion. So he just put in a specific value of 0. Let's look in the table here for a second. So if I put one of them in y1, one of them in y2, looking at 0, I see that they are equal. But looking at every other value, they are not equal. So John lucked out and he found the one value of x that they're equal for. But every other value of x, they are not equal for. So to prove something is equivalent, you can't just pick one value and plug it in. It has to work for all of the values. So to be equivalent, y1 has to equal y2 for all the permissible values. So to summarize my lesson, equivalent expressions can be made by multiplying or dividing numerator and denominator by the same number. You cannot create equivalent expressions by adding or subtracting. So I hope this lesson on fractions was useful. Just remember that fractions speak louder than words. So when you're done, you can go on to assignment 1 to 10 in your workbook. I hope this lesson helped, and I look forward to seeing you for the next one.